Hello YouTube, and welcome back. Here's our solution for 2016 BC2. At time t, the position of a particle moving along the x-axis, in the xy plane, is given by the parametric functions x of t, y of t, where dx dt is given, and the graph of y consisting of three line segments is shown in the figure above. At t equals 0, the particle is at 5, 1. So in other words, x of 0 is 5 and y of 0 is 1. Find the position of the particle at t equals 3. Now the easy part here is finding y of 3 because it's staring you in the face. Look, this is y of t. So what's y of 3? Isn't it negative a half? Look, this point, this is a line segment, they said, right? So this point is at 2, negative 1, and this point is at 4, 0. Isn't the slope positive 1/2? So, right, up 1 over 2. So if we're at the point 2, negative 1, then if we go over 1, we're going up a half. So it's at 3, negative a half. So y of 3 is negative a half. But how do you get x of 3? Well, here's x prime. Isn't the integral from 0 to 3 of x prime x of 3 minus x of 0? And if we're given x of 0, shouldn't we just add it on to the integral to get x of 3? That's what we're going to start with. Okay, so here we go. So let's see here. Let's put a little comment here with your name and the date. And the topic is 2016 BC2. All right, so let's do question 2, part A. Alrighty, so let's figure out. We already know that y of 3. Let's write down what we got. We got y of 3 is negative a half, right? Okay. Let me see if that's what I have here. Whoops, let me look at my notes. Yes, negative a half. Okay. And now I want to get x of 3. So didn't we say that's going to be, how about this? How about if I write down, see, a lot of these questions are going to use x prime. So instead of writing it over and over and over again, let me just type it out. X prime of t, just to give it a name, because it's not x of t then, is given as t squared plus sine of 3t squared. Remember, the multiplication is not implicit in Sage, okay? And just for fun, let's show x prime of t. Make sure we typed in everything correctly, and we're good. Now, the thing is, a lot of times it doesn't recognize t as a variable. It probably does because I did this last period, so don't forget to var t if you have to. All right, there you go. Now that's not really what I want to show. What I want to show is the integrate of that with respect to t, from 0 to 3. All right, let's see what that does. And it's some god-awful number involving earth and I and so forth. What if we want to do just a decimal, nify it? .n function, numerical function. And there you go. But don't forget, that's the integral. Now the integral is x of 3 minus x of 0. To get x of 3, we have to add on x of 0. X of 0 is given. It's 5. So let's add 5 to that. 5 plus that. And so our answer for x of 3 is going to be about 14.377. Let's write down our response here. X of 3 is about, I don't have a good symbol for about here, 14.377. Remember to round off to 3 places when you get wacky decimals. Okay, that's it. Good. That's part A. All right, part B. Find the slope of the line tangent to the path of the particle at t equals 3. All right, now at t equals 3, y prime we said is a half, right? We said y of 3 is negative a half, but y prime, the slope here is at when t is 3, anywhere from 2 to 4 actually, is a half, right? Now, how do you get the slope of the path? The slope of the tangent line to the trajectory of your curve here when t is 3? Dy dt over dx dt. Now here's dy dt, we just said is a half, but dx dt, this is it. But we want to evaluate that when t is 3. Okay, so let's do so. So, 2b, let's see. we're going to try and figure out dy dx. Let's find out what that is. How are you going to figure that out? Show. All right, now, it's going to be 0.5 for the slope of that line segment for dy dt over dx dt, but dx dt is xp of 3, isn't it? All right, so what we get. And it wrote it out exactly because that's what happens when you plug in 3 into t squared plus sine of 3t squared, right? Okay, I don't want that. I want a decimal. So, what do I get? Well, let's see. Let's nify that. Now, if I just nify the denominator, is that enough? Or do I have to put parentheses around the whole thing? So a decimal divided by decimal. There you go. It's approximately 0.050. So let's write that. 0.050. Done. All right, so that's dy dt over dx dt when t is 3. All right, what about part C? Part C says find the speed of the particle. Well, the speed of the particle, isn't that, take the coordinates of the velocity vector, which we just figured out, x prime of 3 and y prime of 3, and do the magnitude of the vector, the distance formula, square root of x prime of 3 squared plus square root of the quantity, x prime of 3 squared plus y prime of 3 squared. All right, so let's do that. All right, so this is number 2, part C. We're going to try and figure out the absolute value or the magnitude of the velocity vector v of 3. We're going to find out what that is in a minute. Okay, and what is it? Well, isn't it, let's see, let's show the square root of, okay, now, it's dy dt, which we said was 0.5, so 0.5 squared, the quantity squared, plus x prime at 3 squared. So x of p, xp of 3 quantity squared. Okay, which in fact are the same values we have here, dy dt and dx dt, in my, to get dy dt when t is 3. So let's evaluate that. And again, that's the exact notation, so let's do that n. And we get 9.969. Okay, there you go. So it's about 9.969. There you go. Perfect. Now, I didn't record this live during class like I did last time because we ran into trouble using the integrate for this part. The integrate command was trying to write the exact, this is a very complicated exact answer in terms of ERF, and then when we unified it just crashed. So I figured we should use something different. How about we use numerical integral? Now, numerical integral is different. It doesn't give you the exact integral or antiderivative and then plug in the numbers and then you can unify it. It gives you a decimal right off the bat because it's doing something akin to Simpson's rule. And so it's just doing Riemann rectangle areas. It's not actually doing an exact antiderivative. So this might be a better idea to use numerical integral instead of integrate here. But by the way, what is part D? Part D is find the total distance traveled by the particle from t equals 0 to t equals 2. Now the problem is from t equals 0 to t equals 2, x prime is always this. It's changing, but it's always this. Problem with y prime is from 0 to 2, it's changing. From here, it's negative. From here to here, it's negative 2, the slope, right? But from t equals 1 to 2, the slope is 0. So if we do the arc length formula, the square root, the integral from a to b, or t1 to t2, of the square root of x prime of t squared plus y prime of t squared, right? The problem is that y prime of t is changing. So I'm not going to do this with the integrate because, like I told you, it gave us a lot of problems in class. Let's go straight to numerical integral. Whoops. And let's do it. Now, I finally got this. What was it? It was 4.350. Let's see if we can justify that, right? Okay. So we're going to do the numerical. Let's see. Show the numerical integral of. Okay, now it's going to be the square root of x prime of t squared plus y prime of t from 0 to 1, remember in the diagram? from 0 to 1, y prime is down 2 over 1, negative 2, right? So it's negative 2 squared. So plus negative 2 squared or plus 4, in other words, right? All right, okay. Now, with the numerical integral, you don't say comma t, comma 0, comma 1. You just say comma 0, comma 1. Okay, so the syntax is different, and what it does is different. It doesn't actually come up with an antiderivative function first and then plug in stuff, right? So let's see what that piece is. Am I missing anything? Hang on. This is the show. This is the numerical integral. This is the square root. Oh, I didn't close the square root, did I? Okay, it's square root of this. So then I don't need that. All right, so that's the show. Something screwy. Wait, hang on. That's the show. That's the numerical integral. What did I do? Oh, why did I put that there? That's the squirt. That's the numerical integral. That's the show. Aha, there you go. All right, so this piece is how much? Yeah, man. And now notice the output. It's a list, even though it's not in brackets. It's usually in the brackets to show that it's a list. This is answer sub 0, and this is the answer sub 1. Answer sub 0 is the area, the Simpson rectangles, right? The Simpson's rule or some kind of Riemann sum. And this is how accurate it is. Look at the error. It's 2.484-ish times 10 to the negative 14th. So move the decimal 14 to the left, and he got 13 zeros of errors. So it's pretty darn good. All right, so it's a very, very highly accurate version of Simpson's rule, I think, okay? Now, the thing is, I can do that and then calculate the other one. What's the other one? Let's see. The other one was similar, except we're going from 1 to 2. And we're not adding negative 2 squared, we're adding 0 squared, so like that. And there you go. Okay, perfect. Now the thing is, I want to add them up, right? I wanted to add the arc length from 0 to 1 to the arc length of 1 to 2. So let's do that. Now look what happens. This is a problem. If you take this, Control-C it, plus Control-V it, and then just comment this out, so it's not going to output this. Is this what I want? No, look, it lists the answer from 0 to 1 and how accurate, and the answer from 1 to 2 and how accurate, and makes a whole new list of it. That's not what I want. I want to add this number to this number, okay? So this is what I got to do. Let me get rid of this for a second to show you what's going on. Since it's a list, I can say, give me the 0th entry of the list. That's the answer, and that's how accurate. I don't care about the accuracy right now, so just give me that. So 2.237 and 2.112-ish. Those are the numbers I want to add up. Aha. All right, so let's take this, Control-C it, put it here, plus Control-V it, and I don't need this anymore. And let's see if that's what we want. 4.350, and it does round off to that, the 3 decimal places. And that's it. There's all of BC2. All done. There you go. All right, so I hope that was helpful. All right, bye-bye, YouTube. Have a nice day.